everyone. In this video, we are going to learn about significant figures and how to evaluate numbers to see how many significant figures there are, as well as how to do math with significant figures. So to answer your question, why do we care? Or why is it important to learn about significant figures? You have to understand that any number we look at in science is a measurement in some fashion. Either I'm giving you that number and it represents a measurement, or you took that measurement yourself using equipment found in the chemistry lab, or you looked that value up somewhere and somebody else at some point did experimentation and used equipment to find that value, right? And so because of that, measurements are only ever as accurate as the equipment we use to take them. So if you think about the difference in accuracy between, say, the scale in your bathroom or the scale we use in chemistry labs, you can kind of understand why some values are considered to have more significant numbers in them versus less significant numbers if you have a less accurate piece of equipment. All right, so when we round our values, when we're doing math with them, we have to round to a certain level of accuracy given to us by the numbers that we're using. All right, so there's a couple of rules to pay attention to. Rule number one is that all non-zero digits are considered significant. So if I'm looking at the number 1.23, for example, that number has 3 total digits in there, 1, 2, and 3. None of those digits are the number 0, and so all 3 of those digits are considered significant. So we would say that this number has 3 significant figures in it. All right? That means that when we think about zeros are kind of our oddballs. Any 0 that occurs in a number between 2 other numbers that are not 0 is going to be considered a significant 0. So example that I might give you for that would be the number 1205 or 1205. There are 4 total digits in this number, and this 0 right here occurs between 2 other numbers, the 2 and the 5, that are not 0. And so we would consider that 0 to be a significant 0. The other 3 numbers, the 1, the 2, and the 5, are not zeros, and so they are also significant. Therefore, we would say that this number has 4 significant figures in it. All right? Next rule are placeholder zeros. Placeholder zeros you can define as a 0 you could get rid of by writing a number in scientific notation. So let me just give you a quick example. The number 12,000, right? I could also write that number as 1.2 times 10 to the 4th. So do you see now how these zeros went away when I wrote that in scientific notation? That means that they are placeholder zeros. Okay, so that, again, if you're wondering what I mean by that, that's what I mean by placeholder zeros. All right? So the number 12,000, let's take it again. If I write that number out in standard form, it has a total of 1, 2, 3, 4, 5 digits in it. But those placeholder zeros at the end, since I can get rid of them in scientific notation, they are not considered significant zeros. So this number actually only has 2 significant figures in it, not 5. All right? We could also look at really, really small numbers if we wanted to. The number 0.0002. I could also write that number 2 times 10 to the negative 4th, right? So all of those zeros, I got rid of them with scientific notation. And so that makes them placeholder zeros and therefore insignificant. So this number is actually only going to have 1 significant figure in it. All right? Our last rule is perhaps one of the hardest to understand, and it states that final zeros after a non-zero decimal are significant. Okay? So what I mean by that, take the number 1.200. mathematically, if we look at that number, it doesn't seem like we need those zeros, right? Because mathematically, you know that the number 1.2 and the number 1.200 are the exact same number. But if you think about this in terms of accuracy and in terms of measurement on, say, a scale that you would use in chemistry, these zeros do have importance. Because imagine you had a scale that said, hey, your item is roughly 1.2 grams, right? And then you had another scale and you weighed the same item and it told you that that thing was 1.200 grams. That second scale is far more accurate. And so those zeros have importance in science if we think about this through the lens of measurement, right? So the number 1.200 actually has 4 significant figures, whereas the number 1.2 would only have 2 significant figures. All right? At this point, you could pause the video. You can attempt the practice problems on your own to see if you get it right. You can watch me go through them. Doesn't matter to me. If we look at our first number, 3.002, there are a total of 1, 2, 3, 4 digits there. 2 of them are non-zero digits. 2 of them are zeros that come between non-zeros, so that number is going to have a total of 4 significant figures. Our second number, 12,000, has a total of 1, 2, 3, 4, 5 digits in it. But I could get rid of these 3 zeros by writing that number in scientific notation, making them placeholder zeros and therefore insignificant. So this number only has 2 significant figures. The number right below it has a total of 1, 2, 3, 4, 5, 6, 7 digits in it, excuse me. Now, this number 3, that 12,000.00, is very different from number 2. Because why would we include that 0.00 unless we were trying to tell you a level of accuracy? So all of those zeros, those 5 zeros, are actually considered significant zeros. And so we're going to say that this number has 7 significant figures, the 5 zeros and the 1 and the 2 as well. Number 4, the number 0.009 has a total of 1, 2, 3, 4 digits in it. I can get rid of all of these zeros by writing that number in scientific notation. Therefore, this number only has 1 significant figure in it. And then last but not least, the number 12 has a total of 2 digits in it. None of them are 0, so that number is going to have 2 significant figures. All right, moving on to math with significant figures. We have 2 rules to pay attention to. Our first rule is for addition and subtraction. So if you're doing addition or if you're doing subtraction, you're going to be using this rule. It states that your answer in a math problem should have the same number of decimal places as the original number in the question with the least amount. Okay, so again, a little bit of confusing, but let me point out what that means. Let's say we're doing the problem 1.12 plus 2.3. If I plug that into my calculator, I'm going to get 3.42. But we need to ask ourselves, do I need to round this answer off at all to match the accuracy of the numbers in my question? And yes, in fact, you do. So the number 1.12 has 2 decimal places in it. You can see them. So I'm going to write that down, 2 decimal places. The number 2.3 only has 1 decimal place in it. My rule says that my answer needs to be rounded to the same number of decimal places as the original one with the least amount. So that's this guy right here. It only has 1 decimal place. So I need to round this off to that first decimal place. This 2 does not round the 4 up. Since it's less than 5, that 4 is going to stay a 4, and my final answer is going to be 3.4. All right? Our second rule down here is for multiplication and division. That states that if I'm doing multiplication and division, my answer should have the same number of significant figures as the original number with the least amount. So in this case, I'm not paying attention to how many decimal places, I'm paying attention to sig figs as a whole. So let's say I'm doing the problem 3.40 times 1.2. If I plug that into my calculator, it's going to give me 4.08. Again, I have to ask myself, where do I need to round that value? So I need to evaluate my two numbers in my question. This number has 3 total digits. That last 0 here is a 0 after a non-zero decimal. So it is going to count as a significant 0, meaning that this number has 3 significant figures in it. My number 1.2 has 2 total digits in it. Neither of them are 0, and therefore it's going to have 2 significant figures in it, meaning that my answer should have 2 significant figures and match my least amount in my question. In my answer, I'm going to count over 1, 2 places, and I'm going to round to this place. The 8, being more than 5, is going to round that 0 up to a 1, and my final answer is going to be 4.1 with 2 sig figs. Once again, you are free to pause the video and try these problems on your own, or you can watch me do them either way. Our first problem here is in the addition and subtraction section, so we're going to be using our addition and subtraction rule, which is all about decimal places. If I plug in 56.7000 plus 345.2 in my calculator, I need to round off that answer to the same number of decimal places as the lesser amount. So this one has 4 decimal places, whereas this one only has 1 decimal place. Therefore, my answer should only have 1 decimal place, and I'm going to round that off to 401.9. All right. For problem number 2, I have the number 12,000, which has no decimal places in it, and I have the number 768.09, which has 2 decimal places in it. Therefore, my answer should have no decimal places whatsoever. If I plug in this problem into the calculator, I get 11,231.91. But remember, that answer should not have any decimal places in it, so we're going to round it off to the ones place. The 9 is going to round that up to a 2, and so my final answer is 11,232. For problem number 3, mathematically, the same exact question, but this time, this number has 1 decimal place, and that number still has 2 decimal places. So again, if I plug that into a calculator, I'm going to get 11,231.91. But this time, since I'm rounding my answer off to 1 decimal place, I'm going to round to this place instead of the ones place. This 1 does not round that 9 up, it actually just stays a 9, and so my final answer is 11,231.9. All right, last set of problems, I'm going to be using my multiplication and division rule, which has to do with sig figs, not decimal places. This number has 1 significant figure. This number has 2 significant figures. So my answer should have 1 significant figure in it, which is going to feel very weird to round off to. If I plug 7 times 24 into my calculator, I get the number 168. But if I want to round that answer off to 1 sig fig, that means I'm rounding to this place. That 6 is going to round that 1 up to a 2, and my answer is actually going to be 200, which again feels very weird and very wrong to do, but you're going to need to get used to it. The second problem, the number 14.000 is going to have 5 significant figures in it. The number 2.00 has 3 significant figures in it. when I plug that into my calculator, 14.000 divided by 2.00, I get 7. But according to my sig fig rule, my answer should have 3 sig figs. So I'm going to have to add a little bit of accuracy there and make that answer 7.00 for 3 sig figs. Lastly, problem number 6 down here. I have the number 45,000, which has 2 significant figures in it, and I have the number 112, which has 3 significant figures. I'm going to have to round my answer off to 2 sig figs. When I plug this number into the calculator, this problem, I get the answer 5,040,000. That number has 3 significant figures in it, and I only need 2 in my answer. So I'm going to count over 1, 2 places, and this is the place that I'm rounding. That 4 does not round the 0 up. That 0 is going to stay the same, and so I actually get 5 million. Here's the thing though. 5 million does not have 2 significant figures, and my answer needed to have 2 significant figures, so that's a problem. The way to get around that is to write the number in scientific notation, because I can write the number 5 million as 5.0 times 10 to the 6th, and 5.0 times 10 to the 6th has 2 significant figures in it, just like I need for my question. So we can use that to get around weird rounding stuff with sig figs. If you have any questions about significant figures, please come talk to me.